Hello dear classmates, welcome back to the Sequential ATPG. In this video, we are going to introduce a new test generation technique, the simulation-based method. We will introduce the context algorithm and the genetic algorithm. The idea of simulation-based test generation techniques is to use logic or for simulator to guide ATPG. This is because simulation is faster than ATPG. The basic approach of this method is that we first generate a bunch of candidate test vectors, and the fitness of these candidates will be evaluated by logic or for simulation. And then we select best candidates based on a certain cost function. The advantage of simulation-based method is obvious because there is no need for time frame expansion. The memory management will be much more easier than time frame based method. In summary, the simulation-based method simulate many vectors and choose the best of them. In 1989, Aguero and Chen proposed the context ATPG for sequential circuits. The context algorithm is based on an event-driven concurrent for simulator. It searches for test vector guided by certain cost functions. There are three phases in the context algorithm. First is the initialization phase, the second is concurrent fault detection, and the third is single fault detection. We will introduce these phases in the following slides. First, the initialization phase. We start with arbitrary test vector and all the flip-flops are initially in a known state. We use a logic simulation to evaluate the cost, which is the number of flip-flops in a known state. Trial vectors are generated by single bit change of the current vector. A trial vector is accepted and becomes the next current vector if it lowers the cost. And we will stop this phase when the cost drops below a desired value. Now it's time for a small quiz. For this given sequential circuit, assume that the flip-flop is initially unknown. Given three trial vectors, which are 0, 0, 0, 1, and 1, 0. Please simulate this circuit and decide their cost, where cost is defined as the number of unknown flip-flops. For example, suppose we apply the test vector 0, 0. The output of OR gate is unknown, so J is still unknown, and the flip-flop is still unknown, so the cost is 1. Now please pause the video and work on this quiz. Okay, are you done yet? Now, let's try the next vector, 0, 1. When we apply this vector, the output of OR gate is 1, and J will be 0. After 1 clock, the flip-flop will become 0. So the cost of 0, 1 is 0, because no flip-flop will be in a known state. For the third test vector, again, the output of OR gate is unknown and J is unknown, so the cost is 1. Out of these three test vectors, apparently 0, 1 is the lowest cost, so we will pick the test vector 0, 1 in this phase. Now we enter the second phase, the concurrent fault detection phase. We start with fault simulation of generated initialization sequence, and the detected faults are dropped from the fault list. And then we compute the cost of the last test vector. Here we define the cost of an undetected fault F as the minimum distance of its fault effect to a primary output. Here, the distance is defined as the number of logic gates, and the cost of a vector is the sum of costs of all undetected faults in the circuit. And the trial vectors are generated by single bit change, and we only accept the vectors that reduce the cost. Now let's see an example. Suppose we start from the first trial vector 0, 0. For this stuckcat 0 fault, this test vector does not excite the fault. So the faulty value and the good value are both 0 here. So the distance here is infinity. That means no fault is activated. Now let's try the second test vector 1, 0, which is only 1 bit different from the first test vector. By applying 1, 0, we can now activate the fault. So we have a D here. Suppose that the flip-flop is in state 0. This is a continuation from the previous slide. So that the output of this flip-flop is 0. The output of the OR gate is also 0. So the output of AND gate is 0. And here we have a 1, and output of K is 0. As we can see, the distance from the fault effect to the primary output is 2 levels of logic gates. So the cost of the second test vector is 2. Similarly, the cost of the third test vector is infinity because the fault is not activated. Out of these 3 test vectors, we would pick the second test vector, which has the lowest cost among the 3. Now let's move on to the next test vector. Starting from 1, 0, we will try to simulate it again. Now the flip-flop is 1. This is continue from the previous test vector. So the OR gate output would be 1, and the fault is activated and also propagated through this AND gate. And the J is 0, so K would be D prime. The distance to the primary output is now 0 because D prime has already reached the primary output, which means the fault is detected. Now we can also try 1, 1, which is a single bit change of the first test vector. Again, we also have D prime at the output. So the cost is also 0 here. Eventually, if we want to apply test vector 0, 0, this vector cannot activate the fault. So the cost is infinity. Now we have 2 test vectors to choose. either 10 or 11. They have the same cost. Now, in summary, for this sequential circuit, we generate 3 test patterns. 01 is generated in the initialization phase, and the 10 and the 11 are generated in the concurrent fault detection phase. Now it's time for you to work on this quiz. Given the flip-flop in the initial state 0 and given this stuck at 1 fault, now please evaluate the cost of 3 trial vectors 0, 0, 1, 0 and 0, 1. Please fill in their cost in the table. And which test vector would you pick? Please now pause the video and work on this quiz. Okay, are you finished? Suppose we apply pattern 0, 0. The stuck at 1 fault would be activated and then propagated to the primary output. So the distance here is 0 for the first trial vector. For the second trial vector, the fault is activated, but it cannot reach primary output, so the distance is 1. Finally, for the last trial vector, we cannot activate the fault, so the cost is infinity. Out of these 3 trial vectors, 0, 0 has the lowest cost, so we would pick 0, 0. Have you got it correctly? Now, we will show the need for a third phase in context. Experience shows that test patterns for all stuck at faults are usually clustered instead of evenly distributed. So, in the test vector space, suppose we have this initial vector. We would find many similar test vectors in this region, and then we will move on to another region, and then we will move on to another region. After this test vector has been generated, we are now left with single test vectors which are located far away. This is why we need a single fault detection phase. Now, in the third phase, we start with an arbitrary vector. We can generate new vectors by single bit change to reduce the cost of the selected fault until it's detected. And the lowest cost fault is picked as the selected fault first. In the context algorithm, we propose the cost of a fault at signal line G as follows. If the fault has not been activated, the cost is equal to KCA of F plus CP of F, where K is a user-defined large constant, and CA is the activation cost, and CP is the propagation cost. If the fault has already been activated, then we would choose the minimum propagation cost of I, where I is the set of all the gate inputs to signal G. Now let's introduce the activation cost defined in the context algorithm. The activation cost CA of G stuck at V4 is equal to the dynamic controllability of line G at value V prime. The dynamic controllability DC is very similar to sequential controllability in scope, except that the logic value are now known. For example, given this AND gate with output C and input AB, if output C is 1, when we want to control C to 0, DC0 of C is equal to the minimum of DC0A and DC0B. That means we need to either flip A to 0 or we need to flip B to 0. However, if C is already 0, then we don't need to specify any more input. So DC0 of C is equal to 0. Similarly, if we want to control output C to 1, if C is now 0 or X, then we need both A and B to be 1. So the DC1 of C is equal to DC1 of A plus DC1 of B. However, if C is already 1, then dynamic controllability 1 of C is equal to 0. Similar things can be analyzed for OR gate and the inverter and the primary input. For flip-flop, if output of a flip-flop is different from our specified value, then DC0 of C is equal to DC0 of A plus a large constant. If the flip-flop output is the same as our DC value, then it is 0. Now let's see an example. Given this sequential circuit and the two lines G1 and the G2, the blue values shows the logic value of this circuit. For this signal, because it is already 1, so its DC1 is 0. For this signal, because it's already 0, so DC0 is 0 and DC1 is 4. Because we have a flip-flop here, so DC0 of G2 is equal to a constant K, which is set to be 100. And the DC1 here is equal to K plus DC1 of the input, which is 4. So we have 104 here. For this OR gate, DC0 is equal to the summation of DC0 here and this DC0 here. So it's 100 plus 0, which is 100. And DC1 here is the minimum of 10 and 104. So it's 10. Now let's compare the activation cost of G1 stuck at 0.4 and G2 stuck at 1.4. The former is equal to the dynamic controllability of 1 for G1, which is 10. And the latter is equal to the dynamic controllability 0 of G2, which is 100. Because 10 is much smaller than 100, so that we know it's much easier to activate the G1 stuck at 0.4 than G2 stuck at 1.4. Now we need also to evaluate the propagation cost, CP. Cp of G is the dynamic observability of node G. Dynamic observability DO is very similar to combinational observability. It measures the effort to observe a value on a given node. So as is shown in this table, for this AND gate, the dynamic observability of A is equal to DO of C plus DC1 of B plus 1. For this OR gate, inverter, and the fan-out, these values can be analyzed in the same way. And for the primary output, the dynamic observability is 0. Given this circuit, we can calculate the dynamic observability starting from the primary output to the left. We can calculate them one level by one level. So that we know the propagation cost of G1 is equal to the dynamic observability of G1, which is 1. And the propagation cost of G2 is the dynamic observability of G2, which is also 1. Now, let's calculate the total cost for these two faults. For fault G1 stuck at 0.4, the activation cost is 10 and the propagation cost is 1. For fault G2 stuck at 1.4, the activation cost is 100 and the propagation cost is 1. So we will choose G1 stuck at 0.4 as our target fault to generate our test vector in phase 3. This is because the cost is lower. So in the following slide, we will introduce the genetic algorithm, which is very useful to optimize our test vector generation. The genetic algorithm was proposed in 1975. The general principle is similar to the rule of evaluation, that is, the survival of fittest. In genetic algorithm, we keep a population of feasible solutions. Please note that we don't just keep one solution. We keep a population of feasible solutions. And then the parent population will generate the child's population by genetic crossover or mutation. We select only best children, remove weak children. And then we repeat the above loop for many generations until a stop criterion is obtained. So for test vector generation, we can represent our test vector by bit streams. This is similar to a gene. For example, this is test vector 1 and this is test vector 2. If we want to cross over these two test vectors, we can randomly pick a piece of gene and swap them to generate a child population. This is called crossover. For mutation, we can randomly pick a bit and flip the value. This is similar to genetic mutation. This slide shows the pseudocode of the genetic algorithm. Given a set of initial solutions, we now generate a child population that is n times larger than the parent generation. We can use either crossover or mutation to modify the gene of the parent population. And then we would evaluate and select the best children in the next generation. We will repeat this loop until a stop criterion is met, and we return the best solution of the population. During this process, we will need to decide what is the initial solution and how we are going to do the crossover and mutation, and how we are going to evaluate and select the next generation, and what is the stop criterion. In summary, in this video, we introduce the simulation-based method to generate sequential ATPG patterns. We first randomly generate many trial test vectors, and we evaluate test vector by simulation and pick the best. Because this is a difficult decision, so we would need many testability measures to help us to make smart decisions. The advantage of simulation-based method are as follows. First, we can have better memory management because we don't need time frame expansion. And the second, we can consider timing during the test generation process. And the third advantage is that we can use genetic algorithm to optimize our test patterns. However, there are still some disadvantages. For example, we cannot identify untestable faults using the simulation-based method, and the test length can be longer than time frame expansion. Thank you for watching.